Thanks. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day, and I just pray that you'd help us use this time wisely to prepare for the test, which is soon upcoming, and just to draw together any of our remaining questions, thoughts, and so forth on this material. Lord, in your name I pray. Amen. There are a couple of little loose ends I need to tie up, so let me start out with an example. And so the loose ends, let's say, things that I still need to do. What is an integral solution? Should talk about that. Some of you have already given me some of these, but it was not out of a good place. It was out of ignorance of how to do the integral. But sometimes that's unavoidable, and these are called integral solutions. The other thing is just applying initial data to solve the initial value problem. We actually haven't done enough of those yet. I'm trying to think what else. There's something else I'm supposed to do today. And actually, completely connected with my first bullet point is variation of parameters example. And exactly, the third shall be the first. You'll see what I mean in just a second here. So let's look at a variation of parameters example. Example 1. All right. Now I need to choose my coefficients carefully here. X squared y prime prime plus, what we got here? I don't know, 3x y prime plus something equals to, well, let's say plus y equals to g. Now, let's see here. So I'm going to fill in the blank here in just a second. I'm going to show you how to make a nice example. So we guess to find the homogeneous solution, what do we do? For one of these problems, one of these Cauchy-Euler problems. To find,
you let y equal x to the r.
Right. And that gives us r times r minus 1 plus 3r plus something. And each one of those brings out an x to the r because we differentiate 2 times, right? Which brings down r to r minus 2, but then we multiply by x squared, which brings us back to x to the r. The middle term we differentiate, which brings x to the r down to r minus 1, but then we multiply by x. That brings us back to x to the r. And the third term, we just got x to the r. So we have x to the r in everything after we plug it in so we can factor it out. And what's left over here is the so-called characteristic equation to here. Now, to make this interesting, I think I should make that, let's see here. What do I got? I've got r squared plus 2r. I'm going to have to do a little surgery here. Let's make this a 4. I refuse to commit to a more complicated example. If I put a 4 here, then that gives me a total of 3. If I put a 2 here, the problem isn't too nasty, okay? See, because with that modification, my characteristic equation becomes r squared plus 3r plus 2, which of course is r plus 1 times r plus 2. Not the most interesting example, but an example nonetheless. And so my characteristic values are r equals to minus 1 and r equals to minus 2, right? So which gives me my first fundamental solution, 1 over x, and my second fundamental solution, 1 over x squared. Still, very interesting in the sense that this is something we couldn't have come to, we couldn't have found this in the constant coefficient problem, right? These solutions are not there to find in the constant coefficient problem. So that would just help me construct the homogeneous solution, right? How do I construct the particular solution then here? So this is a little bit, what's the word? Yeah, it's we've got to think back to our derivation of, we guessed that y was equal to, yp was equal to v1y1, right, plus v2y2. And we derived, what did we derive? Equation 10 in your text, right? Section 4 point, I don't remember, 6 or 9. But it's equation 10 in the variation of parameters section anyway. And that, we had formulas for v1. v1 was equal to the integral, if I remember right, minus g times y2 dx over y1 y2 prime minus y1 prime y2, right? And v2, oh, and I forgot something that's actually really important here. v2 was the integral of g y1 dx divided by y1 y2 prime minus y2 y1 prime. Of course, the thing I just wrote in parentheses is nothing more than the Wronskian of w1 and w2. But there's something missing. Something missing that's important, especially for this problem. What goes in front of the Wronskian? That's been 1 for our examples, but it's not 1 for this one. A, right. And the a, b, c in our derivation were actually functions of x, right? For a constant coefficient problem, they're constants. But this is, of course, not a constant coefficient problem, so a is in fact a function, and it's x squared for this example, right? So calculate, note, we have a equals to x squared. We have y1 is equal to 1 over x, right? So what's y1 prime? It's minus 1 over x squared, right? And we have y2 is 1 over x squared. So y2 prime is minus 2 over x cubed, differentiating, right? Hence, what is y1, y2 prime minus y1 prime, y2? That's equal to what? One over x times minus 2 over x cubed, right? Minus, let's see here, minus y1, which was y1 prime, rather, minus 1 over x squared. And then what's my y2? My y2 was 1 over x squared. This should work out with these Wronskians for more interesting things. It looks kind of scary going into it, but if you kind of just calm down, do the algebra, look at it, what do you got? You just got a, yeah, I got minus 1 plus 1. I get a minus 1 over what? X to the 4th, right? So both denominators in V1 and V2 formulas are what? We have A times y1, y2 prime minus y1 prime, y2. That's just x squared times minus 1 over x to the 4th, which is what? It's really just minus 1 over x squared, right? Okay, so thus V1 is equal to what? It's the integral, and let's put in the details as much as we can, minus g. What's y2? Y2 was 1 over x squared, right? And then what's our denominator? It's minus 1 over x squared, right? dx. So in fact, it looks like v1 is just the integral of g dx as it happens. And what's v2? G times 1 over x, right? And then denominator is the same as it was. So that looks like it's just going to be, yeah, minus the integral of x times g dx, yeah. Put this all together, my particular solution is, what is it? It's 1 over x, that's y1, times the integral of g dx, right? Plus 1 over x squared, the integral, I'll pull the minus out here, right? Minus 1 over x squared, integral of x g dx. And this is an integral solution for the particular solution. Like, if you're given an arbitrary forcing function, this is the best you can do. So if the force is not specified, variation of parameters is the way to go. This allows us to generate an integral solution, which is a solution which is written up to an integration. The general solution would be this, right? Y is equal to c1 over x plus c2 over x squared plus, 1 over x integral of g dx minus 1 over x squared integral of x g dx. So there you go. There's the general solution up to an integration. So some of you might find yourself in the position of teaching a differential equations class someday. Who knows? Maybe you do missionary work to Guatemala or whatever, and you find yourself needing to teach a class of fledgling engineers this method. So you want to make up examples for your test, right? So you do this, and then you look at the formula. Then now we can decide what explicit choice of g would make a reasonable test question, right? So you guys tell me, what g could I pick to actually make these integrals like plausible for you guys to actually do? What's that? G equals e to the x? Sure, we could do that. That'd work, because then you could do these integrals. We can integrate e to the x. We can integrate x e to the x. I was trying to be nicer to you guys. I was thinking, I don't know, 1. Right? See, if we have g equals to 1, then you got this one, right? I can do those integrals without like a lot of mental effort. Your solution would be c1 over x plus c2 over x squared. 1 over x times, what's the integral of x? Right, what's the integral of x times 1? Yeah, 1 half x squared, yeah. So it looks like if g equals 1, I'll write it over here so everybody can see it. If g equals 1, then the solution is y equals c1 over x plus c2 over x squared plus 1 minus, plus a half, apparently. Which I guess is totally obvious. I mean, do you really need to do variation of parameters to figure out that the particular solution to this, if I put 1 here, right, do you really need all this sophistication to tell me that the particular solution is a half? I don't think you do, because it's pretty obvious that the constant is 0 for these two terms, right? And to make 2 times the particular solution equal to 1 again, we should choose a half. On the flip side, if we chose you guys' original choice of e to the x, then these integrals are more interesting, right? If g equals e to the x. On the other hand, we'd have y is c1 over x plus c2 over x squared. The integral 1 over x, the integral of e to the x, of course, is e to the x, right? And then 1 over x squared, this one's more fun. The integral of x e to the x is what? It's x minus 1 e to the x plus a constant, yeah? So I think that's x minus 1 e to the x. And so, okay, yeah, I'm fine. I mean, this second case, I don't think, I don't think we would have guessed that just eyeballing the original problem, right? I don't think I can say, I need something that when I multiply by x squared, take the second derivative, multiply that together, and then add it to 4 times x times the derivative of the function, and then add twice the function again. I need to get back e to the x. Oh, I know. 1 over x e to the x plus 1 over x squared times x minus 1 times e to the... No, this cannot be guessed, right? If you can guess this, you shouldn't be a math major. You should try to be a math professor. I mean, you should have a YouTube channel or something, mental math, that you shouldn't be able to do, or something like that. I mean, whatever. But the larger point here, guys, is the integral solution gives us a template for solving not just one problem, but all possible problems with this same homogeneous piece, right? So the homogeneous piece, again, getting back to physics, is dictated by some sort of setup, right, an RLC circuit or a spring mass problem. And then different choices of G correspond to different external forces on the spring mass problem, or different voltages applied to an RLC circuit. That's a way to think about this problem. Anyway, any questions? So there's the example. I wanted to give you an example of variation of parameters without constant coefficients. It's the same song and dance, but I haven't given you a lot of problems to work on it. But I hope you could work this problem or something like it if I was to put it on the test, right? I view this as a challenging problem for you guys, but it's an accessible problem, I hope. I mean, there's a lot to get hung up on the way to the answer, right? I mean, there's like a lot of details here. Applying initial data to solve the IVP. We've already got everything we need to illustrate this second point here, right? So suppose you take my example 1, and let's look at the x squared y prime prime plus 4xy prime plus 2y, and we'll keep it simple, equal to 1. Okay? And we also know that y of 1 is let's say 0, and y prime of 1 is 3. So now I can say find the solution, find the solution to this initial value problem. Actually, this is example 1. Fine, this is example 2. There we go. So we already did most of the work in example 1. We already know the general solution is what? C1 over x, C2 over x squared, plus, oh yeah, a half. Okay, good. So now what?
Well, if you know that y at 1 is equal to 0, you can plug that value. You get this relationship between C1 and C2.
So y of 1 is C1 plus C2 plus 1/2, right, equals to 0. Why is it, you notice that, well, I already put 1 down, but it would have been probably more instructive if I'd put a 2, because then we would have like C1 over 2 plus C2 over 4. You notice I mean, this is divided by 1 squared. I just didn't write it because it pains me to write these things, Okay, anyway, good. What's y prime? That's minus C1 over x squared, right? Minus 2C2 over x cubed. And the 1/2 differentiates away, right? So y prime of 1 is what? It's minus C1 minus 2C2 equals to 3. That's given, right? So let me gather my thoughts here. I've got C1 plus C2 equals to minus 1/2. And I've got C1, I mean, so I just add equations when I see something like this. Adding equation gives me minus C2. The C1s cancel, and I get minus C2 is equal to, 3 minus a half, which is otherwise known as 5 halves. So C2 apparently is minus 5 halves. And then pick whichever one you like. So C1 is minus 1 half minus C2, which is, minus 1 half plus 5 halves, I think, which is otherwise known as 2, because 4 halves is 2. So therefore, in view of that algebra, y is equal to 2 over x minus 5 halves, well, 5 over 2x squared plus 1 half. Any questions about this? I mean, yeah.
I didn't see that last, I think it's a 4 or a y, not 4.
That's supposed to be a y. There you go. Maybe I should stop using y. I should start writing all of my differential equations in Pac-Man or something. No? Okay. What you got against Pac-Man? You got something against Pac-Man? Oh. You'd adapt. So any questions about example 2? All right, let's work another one of these, and then I'll open the floor for questions here. So with y of, let's say y of 0 equals to 1, and y prime of 0 equals to 0, okay? So let's see, what I do typically is I say, okay, so that's lambda squared plus 4 lambda plus, oh, Carl, I meant to put, I really want to put a what there? I want to put a 4. Yeah, it's true. You got me. So that's plus 4, right? Which is otherwise known as lambda plus 2 quantity squared equal to 0. So therefore, I have lambda equals to minus 2 twice, So if you go back to everything we've done, we know that the homogeneous solution should be something like C1 e to the minus 2t plus C2t e to the minus 2t, right? Now you can do the method of annihilators, or you can just use common sense and say, aha, so I should guess my particular solution should be something like AT plus B. Or if you're me the other day, you'd make it AT squared plus BT plus C, but that'd be dumb, right? No need for the T squared here, we just got T. And so what's YP prime? It's A. What's YP prime prime? It's 0. Plug it in. We get 4a plus 4 times AT plus B equals to T. In other words, 4AT plus 4A plus 4B equals to T. I'm not sure I really needed to write down that last step. So you look at the coefficient of T, you look at the coefficient of 1. The coefficient of T, I've got 4A equals to 1. The coefficient of 1, I've got 4A plus 4B equals to 0. So we find that A is 1/4, And this tells me that 4b is equal to minus 1, or b is minus 1/4. Thus, my general solution, and again, the general solution is the one we want to fit initial conditions to, right? I emphasize. Hear me now. Do not try to fit initial conditions to the homogeneous solution. You can do it. You'll find C1 and C2. You're wasting your time. That is not a solution to the problem. The general solution is the solution. And you usually can't fit initial conditions to the particulars. I mean, the particular solution comes with it a particular set of initial conditions. Like here, yp is what? We just figured it out. It's 1/4 t, right? Plus minus 1/4, right? What's yp? So like, what is yp of 0? Apparently it's minus 1/4, right? What's yp prime of 0? It's 1/4, right? As you can see, the particular solution does not fit the initial conditions. And there's no variability in the particular solution, right? It is what it is. It's going to produce that minus 1/4 and 1/4 for position and velocity, whatever, deal with it. It's there. So choices of C1 and C2 fix that, right? There. So the general solution is y C1 e to the minus 2t. So all I'm trying to tell you guys is that we must fit initial data to the general solution. We do not fit initial data to the particular solution or to the homogeneous solution by their lonesome. I mean, it's a combination effort here. So it's this is the general solution right here. And oftentimes in the past, that's been the end of the solution for us because we were not given initial data. Since we have initial data, we can fit and solve for C1 and C2 to accommodate those initial conditions. Okay, so here it is. Y of 0 is supposedly given to be 1. Y of 0 is also C1 minus 1/4 equals to 1. Well, that's nice. Therefore, C1 is 5/4. Well, that wasn't too bad. Now, how about y prime of 0? There you got to be careful, right? So let's work out what's y prime of t. We've got minus 2 C1 e to the minus 2t, right? Plus C2, product rule, e to the minus 2t minus 2, minus 2t e to the minus 2t. Because t e to the minus 2t is a product, right? Plus 1/4. So I differentiated. Now we plug in 0 to the derivative. What does that give us? We got minus 2c1 plus c2 plus 1/4 equals to? What was it given to be? 0. Okay, good. Okay, so we can do the algebra. We already figured out that C1 is, what was it? Yeah, so we got minus 10 over 4 plus C2 plus 1/4 equals to 0, which means that C2 is 9/4. If I haven't made a mistake. You guys doing anything exciting over fall break? Competition. Studying for my test? Good answer. See here. You guys are already ready. You had quizzes. You guys are ready for the test already, right? No? The way I see it, there are really three things that you need to make sure you have memorized with care. The exact equation result, how you find solutions, how you set up particular solutions by the annihilator, right? And then the variation of parameters formulas. These are the three things to me that kind of stick out as things you're likely to not have completely mastered by now. Most of you by now have learned the integrating factor technique. Or maybe you forgot it. I guess that's number 4. Who am I kidding? There's like 10 things. But those are the first 3 or 4 I thought of. So, all right, let's put it together. So the solution to this initial value problem is y equals to 5/4 e to the minus 2t plus 9/4 t e to the minus 2t. And that was what was my particular solution? Oh yeah, plus 1/4 t minus 1/4. And you can check it out that this, it's fairly obvious if you plug in 0, does it work? What happens when we plug in 0? Plug in 0, I get 5/4 minus 1/4, which is 1. Y of 0 is 1. And checking that the derivative works out is a little bit harder, but when I differentiate and plug in 0, that's going to give me like a minus 10/4 from this. This produces a plus 9/4, and then this is another plus 9. So I get a minus 10/4 from this, and I get a plus 10/4 from that, and they cancel and give me 0. So there you go. The larger point here is you shouldn't really be scared of initial value problems. It's just doing what we've already done, paired with finding the actual values of C1 and C2. Without being given initial data, we can't find C1 and C2, right? Here's a problem I never assigned. How about y prime 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 plus 4y prime prime plus 5y prime equals to 0, with y of 0 equals to 1, and y prime of 0 equals to 0, and y prime prime of 0 equals to 0. Why don't I like to assign these problems? Here, this is d cubed plus 4d squared plus 5d acting on y equals to 0. We haven't done that in a little bit. Let me get back to it. So this is d times d plus 4, d squared plus 4d plus 5 acting on y equals to 0. From this, I can get d times d plus 2 quantity squared plus 1 acting on y equals to 0. From that, I see that my solution is c1 e to the minus 2t cosine t plus c2 e to the minus 2t sine t. And then my d is just c3 as a constant solution. So there's the general solution. I'm not actually going to do it, but then you'd have to plug in y of 0, y prime of 0, y prime prime of 0. It's especially unpleasant here because we have products of functions, which means I have to do the product rule. Like this is a nasty problem. And it's 3 equations and 3 unknowns. Right? For example, like y of 0 is what? C1 plus C2 plus C3 as it happens, etc. So I think you guys are engineers. You can solve 3 equations and 3 unknowns, right? But it does require mental effort, and so it's unlikely I make that a test question. I would point out, if you continue down this road for higher order problems, you have to solve n equations and n unknowns to find the initial constants. Well, that's pretty much all I got to say. I mean, that's it for the test. This is what's on the test, up to this material. I mean, you guys can ask me questions about the test. We've got a little bit of time left, obviously. So, yeah.
I was wondering about the homework last night. It was possibly in the wrong section. It was all about
Huh. Let me investigate. Mission, do you remember which mission it was?
5.
I mean, you got calculus 2 is a prerequisite, right?
Well, yeah, but I was from sections like 2 chapters ahead of where we are, so.
Yeah, but you guys, you've had calculus 2. You know how to do series, right? I mean, here, want to know how to solve a differential equation with series? It's really complicated. Assume, no. Assume that y is equal to an x to the n equals 0 to infinity. Plug into differential equation, work out an. There you go. That's how you solve differential equations with series. No, I'm just kidding. It's not on the test, of course, but you're right. We're not there yet. But the solution technique is actually surprisingly uncomplicated. It's just actually that working out an stings a little. You know, kind of like it's easy enough to write the undetermined coefficients. It is considerably more, oh, don't worry, this does not concern you. It's considerably more work to actually find the A, B, C for actual examples, right? So in some sense, the method of series is the same animal. It's kind of like unlimited undetermined coefficients. Instead of having just ABC, you've got A1, A2, A3, and so forth and so on forever and ever. Amen. Come on. You can do it. You can do it. You can do it. Which one were we on? I guess I have, oh, here's our course planner, right? So I had threatened mission 5, you're saying, and you didn't think that made sense?
Yeah.
Okay. Well, that's not helpful. Definitely.
Because I was all stuck in chapter 8.
Oh, yeah, that's an oversight on my part. Yeah, this is definitely not on the test. So this is what you're trying to ask me about, Garrett. Yeah. Yeah, well, here's the caveat to that. No. Well, what I'm trying to see is if there's not a, there might be a Cauchy-Euler problem hidden there somewhere.
I think something's sitting in mission 4 about that.
I have those in mission 4.
Maybe. I've only done the stuff that's going on.
Let me just scan through here right quick. No, is no allowed, is no allowed, is no allowed. Es no bueno. Not for now, 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 not for now. Okay, it's official. Problem 20 is fun, by the way. This is a way to construct a differential equation that has given functions as solutions, but yes? No? Uh-oh. Oh, okay. Mission 4, on the other hand. Okay, so I have Cauchy-Euler problems. Those are definitely fair game. Spring mass. That one's fun. I think I said that one was bonus at the start, though, didn't I? Yowzers. Goodness gracious. That one was hard. I think I worked this one in... Hey, was this a quiz problem?
This was a...
You know, the cool thing is, I just made it up. I wasn't intentionally making it like this. I mean, I was intentionally making it like this to reward you for doing your homework. Guess you'll never know, huh? Let's see here. These secant cube theta, scary. Secant cubed is scary, but the variation parameters formula, which stem from that problem, are not scary. Because they're not secant cubed. They're actually just a sine substitution, or a cosine substitution, and a secant squared. Right? Secant squared should not be a scary integral to you. It scares me if you're trying to solve secant squared with a method of integration. Right? Like integrating by parts to do secant squared or something. It's like, no, it means you're in a bad place. Like secant squared is a basic integral. If you don't know that, and you're trying to do integral of secant squared, there's an indeterminate amount of time it's going to waste for you on the test. I mean, it's not a good thing. Secant squared integral is tangent, right? Because derivative of tangent is secant squared. Armageddon. Fun. Wait a minute, no, not fun. Seems wrong. Okay, so yeah, mission 4 is in. Mission 5, no, not yet. Thank you. Much appreciated. Other questions? Have I posted the solutions to all your quizzes? In course content? I think I did. Yeah. You guys have no math battles. So you're safe from that. Let's see here. I need to get a new battery for this thing. My battery life, I think, is tending towards about a half hour now. Yeah. Yeah, looks like they're all there. So. No questions? Good, we got 20 minutes. Let's start systems. This is not on the test. What is a system of differential equations? And how should we solve it? So if we have something like, say, x1 prime is, say, a11 x1 plus a12 x2 plus a1n xn, and we have x2 prime is a21 x1 plus a22 x2 plus plus a2n xn, and so forth and so on. Xn prime an1 x1 plus an2 x2 plus plus ann xn, right? And then get rid of the and then usually so here we've got, plus f1 plus f2 plus all the way on to fn. Now, of course, you could think about more general problems, but for us here, if we take these together, we can look at aij. This is an n by n matrix. So I'm assuming that the a11 through ann, these are all numbers, real numbers, right? Now here, the f1, f2, fn, these are functions. of time, right? And these x1, x2, xn, these are also going to be functions of t. But there's a big difference between the x1 through xn versus the f1 through fn. Here's the difference. This is given. This is also given. So you're given the f's, you're given the a's. But the x1 through xn, these are unknown, you know? We're trying to find those. To solve a system of differential equations is to find these n functions of time, x1 through xn. And so if I rewrite this, I can rewrite it using matrix notation as follows. x1, x2, xn. So we take the derivative of this column vector, and it's equal to this matrix A11, A12, A1n. The last column is ANN, AN1. So you're the second row, A21, A22, A2n. Last row, AN1, AN2, ANN. So this is a square matrix. Multiplying that by the vector of unknown functions, x1, x2, xn. And then we add plus this vector of given sort of forcing functions. Instead of having one of them, now we got n of them. So what I've just done is to rewrite my system of n differential equations in n unknowns as a matrix column product. And so we have special names. We call this whole thing the matrix of coefficients, A, the matrix of coefficients. This thing we might just call x vector, right? And this guy over here we would call f vector. Over here we've got dx. Tell you what, instead of using x, I just thought of something. I usually do use x, fine. Dx dt. So let me just rewrite it. Rewrite it over here. So rewrite it over here. In other words, the differential equation, system of differential equations is really just this. It's dx dt equals to ax plus f. Okay? So this is the matrix form for system of n ODEs. It's this. I would say it's the standard matrix form. Okay. Now, terminology. If f is identically equal to 0, then star is what? What kind of differential equations do we say star is if f is identically 0? It's homogeneous. Very good. Otherwise, if f is not identically 0, which means if there's any one point even where f is non-zero, it's said to be non-homogeneous. Theorem. If dx1 dt equals to ax1, and well, let's say that let's put a sub I on that. Instead of 1, let's say I. For I equals to 1, 2, all the way out to, let's say, n of them. Then x equal to c1x1 plus c2x2 plus cnxn, guess what? Solves dx dt equals to ax. In other words, in words, what this theorem says is linear combination of homogeneous solutions is a homogeneous solution. Proof. So we're supposed to take d dt of the sum I equals 1 to n of ci xi. So by properties of the derivative and finite sums, we can pull the sum out, right? We can pull the constants out. And we've got dxi dt. But what is dxi dt? We're given that dxi dt is what? It's a times xi. We're given that they're solutions, right? So I can rewrite this as the sum I equals 1 to n of ci times a times xi. But then, by properties of matrix multiplication, which you guys will all study in more depth in your 221 course or your 321 course, whichever you take, you can pull that constant inside the matrix multiplication like so. Sum I equals 1 to n ci xi. And what's that? You guys are sure you don't want any voter registration? I mean, I got a whole stack of them up here. It's very exciting. You guys just don't vote. You don't have to answer that. You know, I mean, various federal regulations, privacy, blah 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 blah. Anyway, x. That is x again. And so what I've shown is I've shown that dx dt is ax, where x is formed by that linear combination, which shows that x, the linear combination of homogeneous solutions, is satisfying the differential equation. Consequently, it's again a homogeneous solution, right? This is not that surprising a claim probably at this point to you, right? The sum of homogeneous solutions is again a homogeneous solution. That's also true for systems, right? What's the general solution look like? What do you think? Theorem, dx dt equals to ax plus f has general solution x is equal to c1 x1 plus c2 x2 plus cn xn plus a particular solution xp, where x1 x2 xn is a fundamental solution set. In other words, it's a set of n linearly independent homogeneous solutions. So this is the general problem. To solve the non-homogeneous problem, we need to find a fundamental solution set, and we need to find a particular solution. All right? This is what we need to do to solve systems of differential equations with constant coefficients. So basically, to give you a sketch of where we're going, we need to develop methods to find the fundamental solution set, right? And then we need to find a method to find the particular solution. It turns out the method to find the particular solution is variation of parameters for systems, right? And we'll spend about 3% of our time on that with systems. Like it is a burp in the course. I mean, it is very momentary. This studying the non-homogeneous problem. We will spend the majority of our time and how you find fundamental solutions for systems. That turns out it's a little bit more involved than it was for the nth order. For the nth order problem, what do? We write down our characteristic equation, and then we just go to our template of solutions, right? We just start rattling them off. It's exponentials, it's sines, it's cosines, it's t times those things, right? And you can see it. For systems, we have to deal with something called eigenvectors. Because systems, in systems with, say, lambda equals to 3 times. What are the different kinds of solutions that you can see from that? Let me show you. I'll rattle them off for you. The one thing we could have is something like this. C1 e to the 3t u1 plus C2 e to the 3t u2 plus C3 e to the 3t u3. We could have this kind of solution. That could be part of the solution. That's one thing that could happen. You could also have something like C1 e to the 3t u1 plus C2 e to the 3t times u2 plus tu1 plus C3 e to the 3t u3 plus tu2 plus t squared over 2 u1. That's another thing that happens with 3 eigenvalues, the eigenvalue 3 repeated 3 times. There's another case. The eigenvalue 3 repeated 3 times also produces solutions like this, e to the 3t u1 plus C2 e to the 3t u2 plus tu1 plus C3 e to the 3t u3. That's another thing that can happen. So this would come from A equals to 3, 3, 3. This would do that. This one would happen if we had A equals to 3, 1, 0, 0, 3, 1, 0, 0, 3. This will happen if we have A equals to 0. This will happen if we have A equals to 3, 1, 0, 0, 3, 0, 0, 3, like that. In fact, these coefficient matrices give me those solutions where u1, u2, and u3 are actually just the so-called standard basis. Or you call them x, I, j, and k in your Calc 3 class, right? So you shouldn't understand this yet. I'm putting the cart before the horse. I'm just trying to show you a little bit to gain a sense of like what we're up against. Even for lambda equals to 3 repeated 3 times, to know lambda is equal to 3 times does not tell me what the solution is. There are 3 different flavor options within that characteristic solution. So we need to kind of come to an understanding of how do we find these solutions, and that's what we'll do after the test. So I think that's enough for you guys. I think I have enough suffering for one day. See here.